Welcome back to the deep dive. For years, if you follow technology at all, you know the story. Deep learning won. It just won.
Oh, completely. It's the narrative. Large language models, computer vision, audio generation.
Deep neural networks have basically conquered every single domain they've touched.
It's been a total revolution, really, sweeping through science, advertising, everything.
That's right. But there is one huge, and multi-trillion-dollar corner of the industry where that revolution hasn't quite landed yet, and that's structured tabular data.
We're talking about the bread and butter of most businesses, the spreadsheets, the database tables.
Exactly. The stuff that runs finance, logistics, inventory, the models being deployed every single day are still overwhelmingly things like XGBoost, random forest, gradient boosting trees.
And that's the big mystery we're tackling today. Why is the picture so much muddier here? We are diving deep into this really definitive benchmark study by Grinsztajn and his colleagues.
Right. They set out to answer this question with just an incredible amount of rigor.
Their mission was to systematically pit those classic ensemble tree models against the very best, the most modern deep learning architectures that are supposedly designed for tabular data.
And the headline result, the part that should really make you sit up if you think deep learning, is this universal solvent for all problems.
After thousands of hours of compute, after tuning every parameter they possibly could,
The tree still won, consistently.
So our mission today is to go past the what and get to the why. We're going to look at the specific inherent architectural reasons, the inductive biases that give trees this persistent edge on medium-sized tabular data.
Okay, so let's start with the benchmark itself, because this wasn't just some quick and dirty comparison.
No, not at all. A lot of the older studies got criticized. People would say, oh, you just didn't tune the neural nets properly.
Right, or the data set was cherry-picked. This team really wanted to put those arguments to bed and give deep learning a truly fair fight.
They did. They built this extremely robust test bed, 45 different real-world tabular data sets.
So not just one domain.
Everything. Credit scoring, clinical data, energy use. And crucially, they focused on the data size that defines most projects out there in the real world.
The medium-sized regime.
Exactly. They capped the training sets at around 10,000 samples.
10,000 samples. That really is the sweet spot for a lot of us. It's, too big to eyeball, but not so massive. You need a huge cloud budget just to get started.
And for the deep learning models, your MLPs, ResNets, and even the newer fancy stuff like FT transformers and Saint, they pulled out all the stops.
What does that mean exactly?
It means extensive random search for hyperparameter tuning. They ran 400 iterations for every single model on every single data set.
Wow.
Which added up to that staggering figure, 20,000 compute hours. The goal was to find the absolute best possible version of each deep learning model.
Okay, so after all that effort, what did the actual results look like? How big was the gap?
It was pretty clear. When you look at the normalized test scores, so, accuracy or R-squared, the tree-based models XGBoost and Random Forest were consistently at the top.
And this was true even against the newer specialized deep learning models.
Yes. That's what's so fascinating. Things like FT Transformer, they did better than a basic MLP, for sure. They closed the gap a little.
But they still couldn't catch the trees.
They still couldn't reach that performance ceiling set by the tree ensembles. In a lot of cases, XGBoost, with just a little bit of tuning, was already outperforming the best-tuned deep learning model.
And this is where we have to shift from just pure performance to, practicality.
Yes, the thing that actually matters when you have to deploy something.
Exactly. As someone who has to worry about budget and how fast we can get a model into production, the accuracy gap is only half of it. What happens when you plot these results against time?
Well, then the superiority of the tree models becomes, and this is a quote from the paper, even more striking.
Because neural nets are just slow to train?
They are. They need more epochs. They have these deep, complex architectures, and finding the right hyperparameters takes forever.
So even if a neural network could eventually, say, tie XGBoost after 100 hours of tuning,
the tree model probably got there in, a few minutes. On cheaper hardware, it's just a different world of efficiency, better performance, faster, and for less cost. That's a very tough combination to beat.
Okay, so we've established the trees are the practical winners. Now for the really interesting part, the deep architectural why. Let's get into that first inductive bias they identified, the smoothness problem.
Right. This really gets to the heart of how these two types of models learn. It's about their default predisposition. Neural networks, because they rely on these smooth activation functions, they have an inherent bias toward learning low-frequency, smooth solutions.
So they're always trying to fit a nice, gentle curve to the data.
Basically, yes.
Yeah.
But here's the question I think you're getting at. Neural nets are amazing at fitting incredibly complex things in images, right? Recognizing a cat from any angle. Why can't they fit tabular data?
Exactly. That seems like a contradiction.
It's because the nature of the data is fundamentally different. Image data often does lie on a pretty smooth, continuous manifold. Tabular data is jagged. It's full of sharp, irregular decision boundaries.
You mean like rules?
Perfect way to put it. It's less like a curve and more like a set of rules. If your age is over 50 and your income is below a certain number, your risk just jumps. It's a cliff.
And that's exactly what decision trees do. They learn piecewise constant functions. They're just chopping up the feature space into these, well, irregular boxes.
Exactly. So the hypothesis is that real tabular data is full of these high-frequency, irregular patterns that trees are just perfectly built to find. The neural nets, with their smoothness bias, really struggle to represent that kind of jaggedness.
And they ran a really clever experiment to prove this. They didn't just state it, they tested it.
It's a beautiful experiment. They artificially smoothed the target variable in the training data using a Gaussian kernel. They basically blurred out all those sharp edges.
And what happened?
The results were crystal clear. As soon as they smoothed the data, the accuracy of the tree-based models dropped markedly. You took away the irregular patterns they feed on, and they suffered.
But the kicker is what happened to the neural networks.
Right. Smoothing the data barely impacted their performance at all.
So what does that tell you?
It suggests the NNs were already struggling so much with the original jagged data that removing the jaggedness didn't really hurt them. They were already defaulting to a smooth, kind of suboptimal fit anyway.
So the takeaway is, just based on the structure of your typical business data, neural networks are starting with a pretty big handicap.
Which brings us to the second big vulnerability. How these models handle uninformative features, or, just noise.
Oh, this is the daily reality for anyone in the field. You pull a data set from a data warehouse and we get 300 columns, and half of them are junk. IDs, timestamps, redundant features.
And you spend so much time on feature selection just to clean it up.
Hours and hours.
Well, this is another place where trees just shine. The researchers showed that for a gradient boosting tree, you could literally remove up to half of the least important features, and the accuracy barely budged.
So it's doing its own feature selection, basically. It just learns to ignore the garbage.
It does. It has an implicit feature selection built in. But standard deep learning models, especially things like a basic MLP or a ResNet, they don't have that protection.
Every input has to go through the whole network.
Every input gets a weight. So to test this, they ran two really smart experiments. First, they did the cleaning for the model. They removed all the uninformative features.
And what happened to the performance gap?
It shrank a lot. The performance gap between the trees and the MLPs got significantly smaller, which confirms that the noise was really holding the neural nets back.
Okay, but the reverse experiment is the one that's, frankly, a little scary if you're thinking about deployment.
It is. They artificially added new, completely useless features, just random noise drawn from a Gaussian distribution.
So pure static.
Pure static. And adding that noise just blew the performance gap wide open again. It absolutely hammered the ResNet architecture.
Wow.
Now, what's interesting is that the transformer-based models, like FT Transformer, they were a bit more stable.
Why is that?
It suggests their initial embedding step offers some kind of protection against the noise. But still, they weren't nearly as robust as the trees.
So for the practitioner listening, the takeaway seems pretty stark. If your data is messy, and let's be honest, whose isn't, the trees have a natural shield. If you pick a standard MLP, you might be doubling your feature engineering work just to get to the starting line. All right, let's move on to the third, and I think the most technically subtle reason for this gap, this whole concept of rotation invariance.
Yeah, this one is a bit more abstract, but it's so important. When we say a model is a rotation variant, we mean that if you take your input features and you kind of mix them all up with a linear transform or rotation, the model's performance shouldn't really change.
And you mentioned this earlier, but for computer vision, that's a good thing, right? I want my model to recognize a cat, whether it's upright or tilted 45 degrees.
Exactly. It's a feature, not a bug. But for tabular data, it's the complete opposite. Think about your spreadsheet. The columns age, income, credit score, that is the meaningful basis. Each one has a specific individual meaning.
And a tree uses those columns directly to make its splits.
It does. But a rotation invariant neural network, it essentially throws all those meaningful columns into a blender. It loses that individual context.
Yep.
Age and income just become feature 1 and feature 2.
So the network then has to try and learn from scratch what the original meaningful combinations were.
Precisely. And that's incredibly inefficient. The trees just get to use that powerful original structure for free.
And again, the researchers designed this brilliant experiment to prove it. They didn't just theorize.
This was the most striking result in the whole paper, I think. They took the data sets and they randomly rotated them before training. They deliberately destroyed that meaningful basis.
And the result was a complete reversal.
A total flip. Once the data was rotated, the neural networks, particularly ResNet, actually scored higher than the tree-based models.
Wow. So the tree's greatest strength, relying on those clean, meaningful columns, becomes their biggest weakness the second you scramble them.
It confirms it completely.
Yeah.
And the NN's weakness, their rotation invariance, suddenly becomes a strength when the input data is already randomized.
It's really elegant. So let's bring it back to those newer deep learning models like FT Transformer and Saint. You said they did a little better. Why?
Well, a key part of their architecture is an initial embedding layer for the numerical features. And that single step is critical.
Because it breaks the rotation invariance.
It breaks that harmful rotation invariance that plagues a simple ResNet.
Hmm.
By first mapping the inputs into a different space, they sidestep that whole feature blending problem. It's probably why they closed the gap, but because they still had that bias towards smooth solutions, they couldn't quite get all the way there.
So this deep dive has, I think, really changed how we should be thinking about this competition in machine learning. We have 3 solid, evidence-backed reasons why these tried and true tree methods are still dominating on medium-sized data.
To just quickly synthesize them again. First, that neural network bias towards smooth solutions just isn't a good fit for the jagged, rule-based patterns we see in real business data.
And second, the simple NNs are just really vulnerable to the noisy, uninformative features that are everywhere, which means more work for the data scientists.
And third, the meaning is, in the original columns, that feature basis is vital, and the rotation invariance in many NNs actively works against that structure.
So tree models like XGBoost just end up being faster, more robust, and structurally a better match for the environment.
And what that means for you, the practitioner, is pretty clear. For your medium-sized tabular data sets, training sets up to around 10,000 samples or so, ensemble tree methods are still the safest, most performant, and frankly, most efficient tool in the box.
You get top-tier accuracy with way less compute cost and tuning headache. But before we go, there's one last little detail from the paper. They didn't stop at 10,000 samples.
That's right. They did a brief exploration into what they called a large-sized regime, bumping the training sets up to 50,000 samples.
And what did they find there?
Well, it wasn't as rigorously benchmarked, but the initial results showed that at 50,000 samples, the performance gap between the neural nets and the tree models seemed to be noticeably smaller.
So that raises a huge question for the future, doesn't it? We know trees dominate today on the data we have, but what if deep learning models are just data-starved at that scale?
What if their power only really kicks in with massive, massive data sets? Will deep learning eventually close the gap and maybe even surpass the trees when we're dealing with tabular data at a scale far beyond today's benchmarks?
I guess the only thing we know for sure is that 20,000 compute hours wasn't enough to settle the debate for good.
The next great deep dive is going to need even bigger data.
We'll see you next time for the next deep dive.